Hello everybody, thank you for joining today. My name is Munam and today we're going to be looking at blackbody radiation. So some of our learning objectives include to define what a blackbody actually is, to understand the link between temperature of an object and its color, and to understand and explain a blackbody radiation graph for ultraviolet, visible and infrared radiation. Now, something you already need to know is what the EM spectrum, the electromagnetic spectrum, actually is. You know, some of its components, some of its features. If you don't worry, I'm going to remind you. But I have also got a video on it, so you might want to check that out. So if you're ready, let's get into it. Okay, so now we want to understand what a blackbody actually is, right? How do we define a blackbody? So a blackbody can be defined as an object which absorbs and re-emits all radiation incident on it. Now let's break down this definition a bit more. So we have an object which absorbs and re-emits. I think that's kind of obvious, but to absorb radiation means to take it in, and to re-emit it means to give it back out. And all radiation incident upon it. Now this word confuses some people, but incident just means acting upon. So if I have a mirror here, right, and I have a light ray incident upon it, that just means that the light ray is heading towards the mirror. All right, same way if I have my blackbody here. So let's use a cube to represent our blackbody. Right, if I have some electromagnetic radiation incident upon it, right, so it's heading towards the blackbody will absorb all of this and then it will re-emit it back out. Okay, so let's label that all. Let's do a different color. So it absorbs and then re-emits. Now, a byproduct of this perfect absorption and perfect re-emission of radiation means that the temperature of, I'm just going to use double B to represent blackbody, does not change. Does not change. And now if you think about it a bit, that makes sense, right? Because say it's taking in 10 units of radiation and then it's giving off 10 units of radiation straight away, the overall change in radiation is 0, right? So it's not changing any energy that's stored within the blackbody. Blackbody stays at a constant temperature. Now, and blackbodies don't actually exist in real life, unfortunately. Don't exist in real life, but the closest example we can get to is the sun. But scientists often use perfect examples of certain things just to help with their experiments, right? Because if you have something to base all your work upon, you can make tweaks here and there to sort of make it more accurate to the real world. But if you try to encompass every little thing in the real world, your model would get super complicated. And it would kind of defeat the purpose of what you were trying to work out, right? So scientists often use perfect models such as blackbodies to aid in their work, right? But in nature, the closest we can get is to a blackbody is to stars, right? The sun. They emit and they absorb and re-emit pretty much all of the radiation incident upon them. But as you know, in real life, you can never get to 100%. So that's why they don't exist in real life. Now we want to have a look at the link between temperature of an object and its color, and this can be done through something called a blackbody radiation graph. Alright, so now let's have a look at the blackbody radiation graph. But first of all, we want to understand that both the wavelength and intensity of radiation depend on the temperature of the object. Now, I've introduced a new word here, intensity. So let's define it. Intensity. So intensity is the amount of power delivered by some like bundle of radiation unit area. So as always, we like equations in physics, so we get I for intensity is equal to P over A. Now what are the units of I? Well, power is in watts and area is in meters squared. So intensity, as you can see on the y-axis of our graph here, is in watts per meter squared. And as always, on the x-axis we have lambda, which is in meters. Now here, this graph here represents to you how the wavelength changes with intensity. How intensity changes with wavelength. Let's have a look at the green hump here. This green hump is in the infrared region. Okay, this is something that you do need to know, because you only need to know 3 regions: the UV, the visible, and the infrared. So the lowest hub here is the infrared region. Now this is usually at room temperature. Objects. So objects. So say this pen, a table, a sheet of paper, all right, they're all giving off infrared radiation. Now remember, humans can't see infrared radiation, which is why you can't tell that it's giving off something, but it is, and the intensity is very low. Then when the wavelength decreases, right, so remember, wavelength decreases, frequency increases, energy increases to the visible range, so the blue line here, visible range, the peak of the wave goes up, so intensity increases, and to the left, wavelength decreases, so intensity is moderate. So this can be, say, a block of iron. That's a classic example, being heated. All right, so like say when you start to heat the block of iron, first it goes a bit red, and then it moves left along the color spectrum all the way to blue, or sort of whitish blue, right? And that is the hottest that the iron can get without melting, right? But another more common example is the Bunsen burner. You know that the blue flame on your Bunsen is hotter than the red orangey flame on your Bunsen, and that corresponds with a shorter wavelength, because remember, blue light has a shorter wavelength, greater frequency than red light. Then we finally get all the way to red. This is in UV, the ultraviolet spectrum. Actually, you know, I haven't even labeled it on the. Let's do that here. Visible. Let's do this here. UV. Now, this is the sort of dangerous radiation that we get from the sun, right? It can cause skin cancer. This is because it's very intense. Okay, and again, UV, we can't actually see it, which is why it's so deadly. Like, you might be exposed to so much UV. Like, this is why they say to wear sunscreen even when there's clouds out. Like, alright, although you can't see the radiation coming down towards you because its wavelength is too small, it's very intense, which is why we have to protect ourselves. So now we understand how wavelength and intensity change depending on temperature of object. But talking about colors, you also need to know that going that black, so this isn't even technically a color that's present on the spectrum, it's really the absence of color. Black is an extremely good absorber, which is why they say not to wear black on a hot day, but it's also a very good emitter. This is one of the reasons why we talk about black bodies, you know, perfect absorbers and emitters of radiation. Whereas especially matte black, right? Shiny black is better at reflecting. Then we also have white. So these are 2 colors that you should be aware of. White is a very good reflector, but not a very good absorber. But okay, so these are 2 things that you need to be aware of for your GCSE. But now you understand how to draw a blackbody radiation, so how to interpret a blackbody radiation graph, how wavelength and intensity change with temperature, and also what the definition of a blackbody. Well done. Now let's have a look at some things that determine the temperature of the Earth. So let's draw a crude diagram here, right? We have our sun. So let's give it a smiley face. And then we have our Earth here. You know, bit of green, bit of blue. All right, close enough. Now the sun emits infrared radiation towards the Earth, right? Well, it emits in all directions, but some of it gets sent to Earth. If the Earth was a perfect black body, all of the infrared radiation incident upon it, it would re-emit back out into space, right? And the temperature of the Earth would stay constant. Okay. If let's do it in black. If it's a black body, double B, temp would stay constant. But that's not really the case, is it? We've all heard of global warming. We understand the temperature of the Earth is rising, but why is that? Well, let's draw a cross section of the Earth. Here we have our Earth here and our Sun here. Right. The Earth is surrounded by something called the atmosphere, right? And let's draw that in blue. Now this is a layer of gas surrounding the entire Earth. Okay, so that means that when infrared radiation is incident upon the Earth, rather than all of it being re-emitted out, some of it gets reflected back towards the Earth. So that this means that during the day, when infrared radiation from the sun is being incident upon the Earth, right, temperatures are actually rising. Okay, because some of the instant radiation, rather than just being emitted back into space, is actually being reflected by the atmosphere into the Earth and being kept in. It's causing temperatures to rise. But at night, when infrared radiation isn't incident upon the Earth, or that side of the Earth rather, all of the radiation is sort of just leaving the atmosphere, and temperatures are falling at night. Okay, so temperatures are not constant at all. Now, what makes this worse is that greenhouse gases such as CO2 and actually water vapor is actually a greenhouse gas as well, although we often don't think it is, but it is. Water vapor is also a greenhouse gas. Greenhouse gases such as carbon dioxide and water absorb radiation and re-emit it back towards Earth. So why is this a problem? This means that if the concentration of CO2 and water vapor increase in the atmosphere, more and more infrared radiation from the sun is absorbed, captured by those greenhouse gases, and then re-emitted towards Earth. So you end up getting, let's actually do it in green so you can see the difference. You get more and more radiation staying towards the Earth, causing temperatures to rise. And that's how global warming happens, and how the temperature of the Earth is dependent upon the composition of gases in our atmosphere. Now let's have a look at our worked example. Students often struggle with worded examples, so we're going through one now. As always, we're going to highlight all of our key terms. 3 identical pieces of metal are painted different colors: black, grey, and silver. Okay, the metals are placed in equal distance from a radiant heater, as shown in figure 1 below. Ball bearings are then stuck onto the plate using small pieces of wax. The heater is then turned on. Explain what you expect to happen. Now explain. And we can also see that this is 3 marks. 3 marks meaning that they're expecting 3 separate points. Now let's have a look at the 3 different plates. There's a black metal plate, there's a grey metal plate, and a silver metal plate. From our knowledge about black bodies, which one of these is the best absorber and emitter of radiation? That's the black, right? So let's state that straight away. Black is a good emitter and absorber of radiation. Now, this point in of itself isn't enough. We have to compare this to another thing present in the picture here. Let's compare it to the silver metal plate. Silver is not a good emitter, and it is a better reflector of radiation. Okay, so that's 2 points. Because remember, silver is closer to white than, black is closer to white. So we can treat silver as a sort of white and a black as well, black. But now, explain what you expect to happen. If black is a good emitter and absorber of radiation, so black is going to absorb the radiation faster. That means that it's going to transfer that radiation to the wax, and that means that the wax is going to melt faster. So we can expect the ball bearing on the black plate will fall first, then grey plate, then silver. And that right there is our 3 marks for the exam question. If you got that, well done. Now let's have a look at this worked example. Here we have figure 2 shows a heat sink from a CPU of a computer. During normal use, the CPU gets very hot. The heat sink is painted black. Right, heat sink. Explain why. Now remember, it's 2 marks. As always, we're highlighting all of our keywords. Now, you might be wondering, I don't know what a CPU is. You don't need to know what a CPU is, because here, all you need to understand is what a heat sink is. And if you've never heard the word before, well, let's try and work out. Heat, you know what that is, thermal energy. And sink. Sink means to absorb and take away. Absorbs, then takes away. So a heat sink is really something that takes in thermal energy and then dissipates it out into the surroundings. And the CPU of a computer, CPU stands for Central Processing Unit. If you're interested, it's really the brains of the computer. Now, here we know in the question that the CPU gets very hot. Okay, that's our first clue. The heat sink is painted black. Explain why. Okay, so first of all, we want to explain why it's black. Well, it's black because black is a very good absorber and emitter of energy. Well, actually, let's say radiation. Always use your keywords. That's our first mark, but let's explain why it's why the heatsink specifically. Like, what is the job of a heatsink? To take heat away. So it being black and it being a very good absorber and a re-emitter of radiation means that it can dissipate thermal energy from the CPU, effectively keeping it cool. And that's it. That's our 2 marks right there. If you got that, well done. If you didn't, try a few more questions like this and you'll soon get into the hang of it. They're always based on the same basic structure, right? First, explain why the specific color was used or wasn't used, and that's always got to do with its properties of it being a good emitter and absorber or a bad emitter and absorber, and then apply it directly to the use case itself. Why is it in this specific use case? What's the object actually being used for?